Okay, we're back, and this time we're going to be looking at some E&M. We're going to be looking at basic resistor circuits, electric circuits, and a combination of kind of like the rules behind circuitry and the concepts in a big way. The thing I have in mind for today is an example of a network of resistors. We can think of them maybe like light bulbs. Okay, light bulbs can represent as resistors on a circuit diagram. And we want to rank the brightness, okay, the order of brightness from brightest to dimmest of all these different light bulbs. And if they're identical light bulbs, if they're identical resistors, that means we have to try to figure out how much current is actually flowing through them. That will determine the actual brightness of the bulb. So to do anything with resistor circuits, we have to know our 5 rules. Okay, the things we use over and over and over again, no matter how weird or crazy the circuit or problem might seem. We have to know how to add resistance in series and parallel. And for series, of course, that's going to be just the simple sum of all the individual resistors all in a line, all in the same chain. The parallel resistors are the ones that have that weird, we have to add up the reciprocals. You add up those fractions of each resistance on each branch that you have in parallel. And then we have to flip over that answer, flip over that sum. Ohm's law, which might be the most famous of these rules, V equals IR, that's the connection between the big 3. Voltage, you need battery, you need power for a circuit. The resistance, which you can't avoid, that's in every circuit that we use. And then the current, okay, and that's really the current that we're after today. Then we have Kirchhoff's rules. In series, if you add up the voltage losses of all the resistors, all of your components, those voltage losses have to add up to the voltage put in by the battery. Use up all that energy, all that voltage by the time you get back to where you started. And in parallel, when you split a current multiple ways, the sum of those smaller currents on the branches always have to add up to the total current you put in. Okay, you're not going to lose current when you split it like that. Just using those rules, here's a goofy, crazy looking network of resistors. Okay, again, think of each of these as a light bulb. They have equal numbers of ohms. Okay, they're equivalent. And our job is to figure out how the current is going to split when you have these different parallel sets. Now, conceptually, we have 2 light bulbs, 2 resistors hooked up directly to the battery. So whatever the total current is, we'll just call that I, is going through those 2. So maybe let's label these different resistors here. I'm going to start off on the top left. How many is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 13 different light bulbs, 13 different resistors here. We have to try to rank these now. So it's pretty clear that 1 and 13 are going to be the 2 brightest ones. They have the full current going through them. All the others are on parallel sets. They're all on portions of the circuit where that current is going to get split into smaller pieces. How in the world can you figure out and compare all of these to each other to get the actual brightnesses? Well, we have to make use of all of our rules, basically. What I'm first going to do is just try to find, for each parallel set, the equivalent resistance. Okay, so for example, this top set up here, I have to use the reciprocal rule for parallel, but now the other 2, 3 and 4, those are in series with each other. That's 2R on that branch. Okay, and if we do this, and you can check my math here, this should be 2/3 R. Okay. Now let's go to the bottom. That one doesn't look too bad. That's just going to be 1 over R plus 1 over R. We have to flip that over, so that'll be 1/2 R. That's the equivalent resistance for those two. And then, of course, we've got this on the right-hand side, this kind of beast of a little network here. So we have three different branches. If I do my parallel rule, that first branch, 5 and 6, are in series with each other, so that's going to be a total of 2R. The middle branch, 7 and 8 are in parallel with each other. And just kind of like we saw with resistors 11 and 12, that's equivalent to a half times R. That's going to add to resistor 9, which is R, so that's going to be 3/2 R total on that branch. And then we just have a single resistor on that third branch. All right, now if we add all of this up and flip it over, I got something like 6/13 R. Okay, you get funny fractions when you do circuit problems. Why am I doing this? Why am I finding the total resistances for those parallels? Well, one thing I always teach my students to do when you have parallels, especially multiple parallels, is to redraw the circuit. I'm going to draw it as a series circuit down here. Okay, series is just easier to work with. It's easier to look at and try to figure out. So I'm going to take these total resistances we just found and put them on these resistors down here. The top one was 2/3. We had this funny 6/13 R over here. And then we had a 1/2 R down in the bottom. And then those other two standalone resistors. Okay. The beauty of doing this, and the reason for doing this, is because now in series, your total current is going through everything. We don't really care what the total current is. Okay, it's just whatever number of amps. That doesn't matter so much since we're doing this symbolically. But what we can do down here is the following. We can go ahead and we can find the voltages, the voltage losses on our parallel sets. Okay, so for example, using Ohm's law, the voltage of a resistor is the current going through the resistor multiplied by the resistance. So if a total current I is going through 2/3 R, we just multiply those together, and that'll tell me the voltage up here, 2/3 IR. On the right-hand side, I times 6/13 R is 6/13 IR for the voltage. Down on the bottom, we'll have 1/2 IR. Okay. Those are the voltages on those light bulbs, on those resistors, which is equivalent going back up to the real thing. Remember, in parallel, the beauty of parallel and the miracle of parallel is that branches are at the same voltage. Okay, so let's go ahead and take the bottom one, okay, that 1/2 R. I'm going to take this voltage down here and transfer it up here to say, okay, well, each of these resistors, each of these light bulbs is at a voltage of 1/2 IR on the bottom branch and on the top, and on the top branch, 1/2 IR. They're in parallel, they have to have the same voltage. What's the current? Well, Ohm's law also says that current is the voltage divided by the resistance. So if you have 1/2 IR divided by R on the top branch, that's going to tell me that the current going through is 1/2 I, 1/2 the total current. And through the bottom, it's 1/2 I. We're dividing those voltages in black by R, by the resistance on the branch. And that's what we'd expect. Okay, if you have two equal branches, two equal resistors, the current's just going to split in half, and it shows that. Okay, if we do it on the top one up here, okay, each of these is at 2/3 IR for the voltage. Now, the bottom branch, I'm going to think of these two together as just a single resistor of 2R. And the voltage of that resistor is 2/3 IR. Now divide these out. Use Ohm's law, voltage divided by resistance. And what you get on top, 2/3 IR divided by R is 2/3 I, 2/3 your total current. 2/3 IR divided by 2R. On the bottom, you get 1/3 I, 1/3 of the total current. Those add up by Kirchhoff's rule in parallel. Those currents have to add up to I, the total current, and they do. Okay. So now we're figuring out. So we're figuring out the fractions of the total current going through all of these different branches, all of these different light bulbs. Okay. Now the crazy part. I'm going to think of this left branch here as a 2R resistor. And let's remind ourselves, what voltage did we have? Well, we've got 6/13 IR. Okay, so let's, coming down this left branch here, we have a voltage of 6/13 IR divided by 2R, okay, the resistance on that branch. And that, the R drops out and a factor of 2 drops out. That's going to give us 3/13 I. Okay, funny number. Let's take the far right branch over here. Same voltage, right? 6/13 IR. It's in parallel. All the branches have to have the same total voltage. Divided by R, you get 6/13 I for the current. Okay, just a little bit less than a half of the total current goes down that branch and through that light bulb. Now coming down the middle branch, okay, remember the total resistance here, we can think of that branch as having 1.5 R, or 3/2 R total. But the voltage is 6/13 IR. So what happens if we divide these out? Well, the R drops out, a factor of 3 drops out, and if you do the math, you get 4/13 of the total current. That's coming down that middle branch. Now, add those currents up. 3/13 I, 4/13 I, 6/13 I. Add those up, and you get 13/13. So you get the total current. So it looks like we split up properly. The last piece of this, though, is notice that in the middle branch, the 4/13 is going to split through those two light bulbs, those two resistors in parallel up there. Okay. How's that going to work? Well, it's the same resistance. You could just say, okay, it's going to split in half. And so we're going to have 2/13 of the total current going through each of those. Now we have it all. Look at this mess. These get really messy in a hurry. But I think we've identified the following, so that the two brightest light bulbs with the total current going through are 1 and 13. Those are the brightest. What's the next brightest? Well, which of all of this mess here has the next highest fraction of the current? Well, it looks like this one up on the top, with 2/3 of the total current going through. Okay. That looks like the next highest fraction. Then we're going to have, look at all these different fractions, it looks like 1/2. So 11 and 12 down here. Those are going to be the next brightest. Then we look at the far right, 6/13, just a hair under a half. Okay, so resistor 10 will be next. Then a little bit dimmer is going to be the 4/13 I. Okay, or light bulb 9 down there. Then it looks like the okay, I may have, hold on, I forgot one up here. we have 1/3 I up here. It looks like resistors 3 and 4 would be next, then the 4/13. Okay, 4/13 is a little bit less than a third. Then we're going to have 5 and 6, the 3/13 of your total current. And then the dimmest ones will be 7 and 8. Those have the smallest fraction of your total current going through them. Okay, it's a mess, but we can do this with just a handful of rules that we apply over and over. If we understand those rules, understand the concepts behind how current works, we can figure weird things like this out. Okay, so I know there's a lot here. If this is kind of new to you, you might want to watch how I work through this a couple times. Go back and replay it. But we can do this by using Ohm's law and Kirchhoff's rules together to find the voltages when you put them in series like this, and use the voltages in Ohm's law to figure out how it breaks down on the individual branches. And that's how you compare the currents in all parts of a circuit. I hope this helps. And until next time, we will see you later.